the copies of the slides.
Did you want the homework?
I will cover it. So if the quality of the image is not satisfactory, you just look into your emails for the slides. And right now we are in the computational chemistry, which is for both graduate and undergraduate students. So the goal of the course is to complement main direction of research that most of you, those who are in graduate school, are already pursuing this computational component. And the course is organized as bringing together some theoretical background, practical skills, which is writing right software on right hardware by computing observables and comparing them to experiment. So by now we are on the lecture 24, and 23 was cancelled due to snowstorm, so I will try to squeeze in into one. So please prepare for intense intellectual effort, right? But do not put all of your energy. Main goal of the course and main assessment is based on how you apply practical skills to real problems. So this is the main thing. And, the theoretical material is just a background to the right methodology section and to take the correct terminology. So last meeting before the snowstorm, there were presentations on practical skills on running DFT on specific software, and we are today. You are on a specific lecture. We are on the border between two chapters. We are completing the chapter of data functional theory, which focuses on the ground state properties, which means a system that was not perturbed by external electric field or electromagnetic vibration, and the excited states which happen if you hammer the system with external perturbation, primarily UV with excitations. So by now we have already started the mini research projects, and while I'm talking, let me collect the homeworks which you did care about. So if you didn't print it, please send it to me as an email. Which is, so the research projects are chosen by participants of the class based on your interests with provisions of your primary advisors. And those who were hesitant and not sure about research project, there were several options to study chemical reactions, properties of nanostructures. So by now in this homework you did have completed, I hope, I will look through, the basic electronic structure of your system of choice without any perturbation. Some of you did optimized structure, some of you just took single point. It is needed as a reference. And in the remaining part of semester, which is like 2 weeks plus something, 2 weeks, right? So here is the plan, what you are suggested to do. Again, everyone is welcome to deviate from this path. Each project is individual. You are experts in the areas and you may modify it substantially, but here are general guidelines that you may choose to follow if you're not sure what to do. So it is an oversimplified protocol for this computation. So you can formulate your mini research project as a response of your model to heat treatment, to like thermalization. And in this aspect, you select your model, optimize geometry, and then do density of states and spectrum, and maybe some other electronic structure features, signatures. In this line, you can also explore anions, cations, and other things. And your homework is basically these 3 boxes that if you...
What if you went the other way?
if you missed to complete them, or if you went other way, do not worry. Main thing is that we get final result. It's and the homework is more like assessment of the progress and a sign for me how to help you, right? And what you are suggested, and again, it is not must protocol for everyone. It's just suggestion in the remaining part of the semester, and do not wait the lab that will be help session tomorrow evening. If you want, you can start right away instead of listening what I mumble, just submit jobs. So take your model and simulate heating and molecular dynamics at a temperature of your choice. And then upon molecular dynamics is completed, find the same electronic structure characteristics of your model in the simplest way, density of states and spectrum. And then you just compare them and derive some conclusions. Why it is interesting what you may observe. So if you heat your model substantially to like 2000 Kelvin. Hi, Anas. Hi, Queenie. Did you distribute all copies, or there was something else? Oh, you better sit and I will serve, otherwise.
Okay.
So the materials are some handouts on So one handout is on the basic equations of DT functionals, and another one is on basis set of plane waves that we are all using. And you didn't miss anything. I was overviewing your research. So you complete your homework, and I'm looking forward to collect, which was ground state features, right? Like density of states and spectrum. And in the remaining time, you heat your system and see what happens. Upon completion of molecular dynamics, you look onto density of states and spectrum. And why it is interesting, what is expected. So if you heat it substantially, and if your system is like very gentle, you can rupture, break chemical bonds, and if you expose uncompensated bonds and show different electronic structure signatures. Some models may stay chemically intact, but they can rearrange like thermoplastics. Some of you are doing polymers.
What could be the reason for having a TT file that equals 0?
If you didn't complete molecular dynamics. So it is 2 different runs. One heating, another molecular dynamics. And they do not have sense without each other. Yes?
So if your system can withstand high temperatures, then you know it's pretty safe. In terms of, and that's where you would check the equilibrium and make sure that.
Yes. And there will be a help session tomorrow evening at 6 p.m. in this lab for assisted processing of this protocol.
You can come here and work early.
You can come early.
Yeah.
I cannot come early.
Oh, sure.
So the little challenging aspect of completing your projects and bringing them to presentable way. So we all are in academia, and we are looking to pull money from feds, get recognition from colleagues, and have papers accepted. So how do you, even if you get nice results, how do you present them? If you follow all the things, you have nice models, and you do anything you can. So it is a challenge. You will, even if you do not invest substantial time into work, you generate much more data that one can squeeze into a paper or written report. So you need to practice an intellectual effort to choose right material and arrange it in a logical way. So here are some suggestions. Again, without it, they are not mandatory. It just shows you directions of thoughts. So it is more than needed. So for example, you may select a property of your model, like band gap or total energy or oscillator strength of the lowest transition, right? And then you can explore your system at different conditions. For example, you can look at your neutral without spin and report the data that you get. And each cell here would correspond to independent run. You can permit your system to be spin polarizable. So if you do have transition metals, results for like total energy can be different here. Then you can withdraw or add electron, simulating acidic or basic environments, and see how the your observable like total energy will change. Typically, if you add electron basic, it will slightly increase. If you remove electron, it will go down, but not necessarily. Some systems, if you add or remove more than one electrons, will form like a parabolic curve with a minimum at most stable situation. Then you can run molecular dynamics and see how the things will look after molecular dynamics. And then you can plot density states, absorption spectrum at each configuration and report them as a figure or fill it into like many panel table. So it is your choice. It's just ideas how to organize your data. Yes?
So if you don't have a transition metal in your system, you just be doing neutral anion pattern.
So this spin polarized is needed if you anticipate that there could be transition metals or radicals.
Ah, okay.
Or if you know from your experimental background that it can be like in a triplet state. If there are any evidence that spins on one of the orbitals will be unpaired.
Ah, gotcha. Okay, I got it.
So
so this is where if you have like an uneven, so if you have like 1.08 whatever in occupied instead of having the 2 orbitals, that could be where you have that.
exactly,
Yeah,
exactly.
okay.
So it doesn't mean that your results without spin polarization are garbage. Maybe they are also very valuable. But if you want to double check, and if you see like the total energy converges in one or another, is a good sign, because without spin it is so much quicker.
Right.
If you can justify that it doesn't bring you any benefits. So now 2 lectures in one. I will try to squeeze through and skip details wherever possible. And some of you were attending online presentation of this material on Thursday, and so for some of you it will be not quite new. So who we are and where we are right now in this course. So Intel, I'm departing from practical aspects from our mini research projects to theoretical background. So we need to completely finish the subject of Bronsted density functional theory in less than half an hour, and then start put into the door for the excited states, or so-called TDT theory. So you all successfully passed some tests and forms of an assessment for reproducing the feedback of the DFT self-consistent for density solve for density and then repeat this loop until getting convergence. Okay? The thing that we are partially missing in the course are functions for dependence of total energy on the density. Right? And the dependence of total energy on the density is called functional. Okay? And the simplest one is local density approximation that we partially cover. So it is just integral of density to the power whatever 4/3 functional integration. All other functions that give better precision than dA are much less pleasant, and they take more than one screen to show equations and even more than one book page. So, and since it is not advanced theoretical course, it's more practical, we are skipping this. But there is a little thing that we really need to add and consider here, how the functions that are allowed to structure the energy of the density behave in case we have spin polarized situation. So if you are modeling stable organic materials, hydrocarbons, with even number of electrons, you may do that and speed for half an hour. But if you anticipate that your material does include transition metals, or may come into triplet configurations, or participate in chemical reactions with open shell configurations, you may watch this little entertainment. So, in the regular density, local density approximation, so rho is density, E is energy, and rectangular brackets symbolize function. So it is rho to the power 4/3, which can be processed as rho to the power 1 times rho to the power 1/3, and then you can submerge this rho under the differential and express it as a functional integral of the density into the power 1/3. Why this notation is important? Because for practical quantum procedure, we need not the total energy, but the potential, which is functional derivative of the total energy over density. And if you practice functional derivative of this expression, we will get rho to the power 1/3. Right? And those are two complementary operations: functional derivative and functional integration. They kind of compensate each other. The same conjugated procedures as regular integration and differentiation in calculus. And here is the equation that will come at the end of the chapter in about 25 minutes or earlier, that will conclude everything about ground state density functional theory. So if you aware, if you have seen it before, or if you do not need it, lean back and relax. For 25 minutes there will be nothing except technical details about this equation. So in case you do have spin polarized situation with unpaired electrons, you have density for spins up and spin down, and their number and their density is not always equal. So there is a spin polarization parameter or spin density, which is subtraction of density of spins up minus density spin down with normalization. And it enters into the expression for total energy. But this combination, this spin density expression, is dimensionless. And it enters the expression for functional as a factor after this rho to the power 4/3, which is like, if there is no spin polarization, this factor becomes 1, and we reproduce the local density functional. Just in case where this local density approximation comes from, and how does it relate to the basic quantum theory that was derived a long time before DFT. These expressions of casting energy in terms of electron density was originally offered by Thomas and Fermi in like 1928, shortly after design of Schrödinger equation, and it was describing the universe where there are no ions, only non-interacting electrons. And there the power was 5/3. And if you want to describe realistic nature, and you just slightly change the power 4/3, and it will be good enough to do good things about molecules. Okay, so what are these notations, where they are coming from? Who never saw a compass? So, what you all saw it. What the arrow of compass is made of? Huh? Which material? Okay. What is feature of iron if you look into periodic table? Mm-hmm. Yeah. So you can deliver a lecture instead of me. So odd number of electrons, magnetic. Right? So there is a correlation between number of electrons and magnetic properties. So if you have magnetic materials, likely number of electrons on a single ion is not compensating. In case you describe a material and you do see that a number of electrons are unpaired, there is a substantial probability that it will respond to magnetic field. And it will be especially boring. 3 slides, fall asleep. If you want to theoretically describe spins, you need Pauli matrices and spin operators. Pauli matrices correspond to raising and lowering spin going up and down, and their linear combinations give connection between operators for raising and lowering spins and the magnetic field. So if one takes expectation values of these 3 operators and practices it, not for simple model for homework in class, but for realistic materials, one can get 3 projections that will give you magnetic field if you multiply it by geomagnetic ratio. And generally, if you have spin up and spin down, or it is often used in notation alpha and beta, one uses wave function orbital with alpha and beta components. So this 2-component orbitals, 2-component wave functions, each of which depends on position, maintain very specific properties of orthogonality, and by multiplying them in the dyadic form, one is getting 4 components of density. So 2 of them would correspond to absolute value square of these wave functions, would correspond to probability of spin up and probability of spin down. And the off-diagonal elements are really needed if you want to model like EPR signal in real time. But it is very challenging problem, or if you want to describe magnetic materials in all of their details. But for majority of practical problems, one skips this off-diagonal terms and considers only diagonal ones, which correspond to probability of electron density with spin up and spin down. So if your system has this unpaired number of electrons, it must respond to magnetic field. And you are accepting the argument about compass, right? The arrow follows magnetic field, and if you approach the compass and try to rotate it against, you need to apply energy. So there is an energy of interacting of this arrow and magnetic field depending on the angle. So the three components of expectation value of a spin multiplied by magnetic field vector will give this energy, this multiplication factor. And if we assume that magnetic field is oriented only along one axis, like z, then we can skip two parts of the scalar product and keep only linear product of expectation value of z component and magnetic field z component. Right? So if the x and y projections of magnetic field is 0. And if we carefully keep sleeping, it's not important. If we carefully following the quantum rules for finding expectation value based on operator and wave functions, or operator and density, then the expectation value of the z component of this spin will be nothing but subtraction of density up and density down. And one also needs to include integration over space. So the difference of the density in up and for electrons with alpha and beta spin projections is naturally corresponding to energy of interaction between this system and magnetic field. So we do not need it. It's only an argumentation why this difference is important. So now Queenie is invited to wake up. Everyone is welcome to wake up as well. So if you remember what Queenie was presenting a week ago, he was showing how to compute density of states for spin polarized case. So our practical steps went a little ahead of lecture theory material. And what Queenie was showing, there are, if you run the software with the keywords corresponding to spin polarization, there are two lists of orbitals, unoccupied and unoccupied. Right?
Yes.
I'm not lying.
You're not.
Thank you. And in each list, you have so many orbitals with occupation 1 and so many orbitals with occupation 0.
Yes.
So here I'm going to refer to what you are doing. So if you have HO sub alpha orbitals occupied in your first list, right? Then you take absolute value square of all orbitals that are occupied, and this will give the density of all electrons with spin component alpha. If you hate density functional theory and you take standard interpretation of quantum mechanics, you should interpret it as probability. That you do have so many density of having some electrons with spin-up component in the point of space R. Then you do have a second list, and you have a specific number of orbitals that are occupied, and these numbers can be different. You also take absolute value square of all these orbitals, and it will be density for spin down. So what is important that these numbers of occupied, highest occupied orbitals with spin alpha and highest occupied orbital with spin beta are not equal. If they are equal, then you do not need spin polarized calculation. You just return next step back and use regular singlet calculations. And total energy is a function of these two densities, spin up and spin down. there is nothing wrong. It is a correct expression. And if you take some basic books on density functional theory, you will see only these expressions. The handout that was distributed formulates total energy in these terms. But in practice, it's not practically convenient. And in the remaining 15 minutes, not for the whole lecture will go until you fall asleep for sure, but the chapter about DFT will be finished in 15 minutes. So in practice, the total energy is expressed not as functional of alpha and beta density, but as a function of their sum and subtraction. You see, it's not a big deal, right? From two variable to functions to their sum and subtraction, it's still two independent functions, but it has some physical meaning, and the expressions for functions become more useful. So, summation and difference. So, if you add together these two densities and integrate it over the overall space. So, if you integrate the density alpha, you get number of electrons anywhere in the space, right? If you integrate beta, you get beta. If you integrate their sum, you get summation of electrons with spin projection up and summation of electrons with spin projection down. So total number of electrons in the system. So it is a standard thing. And if you integrate their subtraction, you'll get difference of up and down, right? So how to interpret this number? How to put it along with your knowledge from undergraduate years? Most of you have taken inorganic chemistry or some parts of it as your chemistry courses, right? Or maybe you are nature remembering things like that from kindergarten. So this number, this difference of spin up and spin down electrons with spin projection up and spin projection down can tell us about the maximal possible spin that this total spin that this system may achieve. Of course, it can come at different angles with different projections, but since each spin is like Pauli Planck constant divided by 2 or just 1/2, then maximal value of a spin will be this difference, dn divided by 2, right? And it can take values like 0, 1/2, 1, 3/2, right? And as soon as you define total spin, if you follow like undergraduate parts on the inorganic chemistry, you immediately go into definition of multiplicity. So if spin is 0, it's not degenerate. If spin is 1/2, it's 2 degenerate, can be up and down. If spin is 1, it's 3 times degenerate, up, horizontal, down. So this is simple equation like 2s plus 1. And s, you plug in just this number. So if it is singlet, you have just multiplicity 1. If it is spin 1/2, multiplicity 2. Spin 1, multiplicity 3. 3/2, multiplicity 4. And some people use verbal labels to this degeneracies, telling like singlet, doublet, triplet, quartet, right? So if you are running spin polarized DFT, you are able to approximately compute states of a system in this singlet quartet. And there is a way to mandate system to stay in one of these spin polarized configurations. There is a keyword in Gaussian, it is spin and multiplicity that you put in front of coordinates. In VASP, it is n up down keyword that sets up. No. Sometimes it is beneficial to normalize things. And if you, instead of using just difference, but difference divided by sum, it will be dimensionless spin density. So it's function of position, and it is a thing that is used in DFT as a parameter for functional. And from this spin density, one can reconstruct back the density of spin alpha and spin beta, right? So if you add 1, find the common denominator, and then cancel this denominator by multiplying by total density, you get alpha. If you have here minus, and you do this operation, you get spin beta. So these two, in 8 minutes, you will be done with density functional theory, and we'll start the chapter. So instead of energy as function null, as functional of densities alpha and beta, you are converting to functional of total density and spin density. And here is the equation we are starting from. So density into power 4/3, or functional with regular integration, or functional integration of density to the power 1/3. So it will be natural to assume, at least it was assumed by people who introduced these functions, that energy contribution from spin alpha and spin beta at lowest order will come by the same type of equations as before. So it will be just spin alpha to the power 4/3 and spin beta to the power 4/3. And we do have, from previous slide, little manipulation, how to express alpha and beta in terms of total density and spin polarization. Right? So we can plug in these two expressions. And if we, so one with spin density +1 and one with 1 minus spin density. And here you do see that both of these expressions have total energy out of brackets. It is separate, it is factorizing spin density. Why don't we put it out of bracket completely? Yes, we can. And then we have an expression with total density in power 4/3, and then this factor that originates from spin polarization, which is dimensionless. So in case you try to apply it to system with in a singlet, or this psi equals 0, this will be just 1. Right? So by now, I think we are coming very close to finishing chapter 1. Here's just a little example how other functionals may look like. You will never need this equation. It's only for illustration. The only thing that we need when we operate software, we just use abbreviations for functionals, right? A very small fraction of theoretical theorists are dedicated and interested in deriving new functionals. For most people who do applied computations, one uses only abbreviations like this one. One takes first initials and year when it is done, and or browses through this list in the drop-down menu in Gaussian software, or uses correct keywords in VASP software. But just to see what it includes, so before we express total energy as functional of density, right? Density defined only in one point of space, local. And the next step, which gives a little better precision, expresses in terms of gradient of density, spatial derivative of density. So it makes a little manipulation for normalization, and then this x means the gradient of density computed at each point of space divided by density. And then there are some reasons for one or another functional form to place this correction into the equation for the potential. But potential is a functional derivative of the density. In the zero order term, when we neglect this correction, it will be just rho to the power 1/3 and some constant. So in the limit we neglect this gradient correction, we arrive back to LDA, local density approximation. So sometimes we need to speak bird's language, to use abbreviations used in the community. And for the class of functions that include correction with this gradient of density, they are called GGA, generalized gradient approximation. And this is one of the simplest GGA functions. Typically they are much more complicated and not pleasant for human eye to follow. And one can continue, it's same as Taylor series. One can get more and more terms with better and better precision. Okay, from now on, you are certified experts. If you are sitting here and you are not objecting against material anymore, you are certified experts in basic functional theory. Okay. So now we need to slowly start a new chapter, a new material. So intuitively, and from your experience in wet lab, you can get an idea that experimental work can be symbolically reduced to two chapters, two different styles of action. One is fabrication or synthesis, another is characterization. If you try to mimic it in the computer lab, synthesis how we build models, and the characterization is different observables that we extract from calculations. So very popular characterization of materials is exploring response of a molecule or material to external perturbation. Very popular is to look the response of a system to electromagnetic radiation as a perturbation. And it deals with promotion of electron from ground state, from occupied orbitals to unoccupied, or more generally from ground state to excited, which can be represented in different ways. Before, in our practical sessions, we were computing spectrum, but it was done in a very strong approximation. We considered independent orbital approximation where we just promoted electron from HOMO to LUMO or some other ways of promotions of electrons between two orbitals. This is lowest order of theories. There are specific theories that add correction to this simple picture. So here is your favorite feedback loop for DFT, right? No one is surprised. You successfully passed homework. And here are the things that typically used as abbreviation if you would do DFT that we just finished. So you may recognize this spin polarization, and you may recognize that's enough. And you may recognize this gradient. And this is what we did before. So what is the main challenge in describing a response of a computational model to electromagnetic radiation? And what is the challenge to describe excited states? So if you have occupied orbitals and unoccupied orbitals, and you have degeneracy, you have two HOMOs and two LUMOs, how do you know if you're promoting from HOMO to LUMO or from HOMO -1 to LUMO +1? Or there are from HOMO to LUMO +1, or from HOMO -1 to LUMO, or they're all excitations simultaneously. So we are partially missing this picture. And another thing, we do know total energy of system when all orbitals below and including HOMO are occupied, and all above are unoccupied. But if we create this promotion of electron from valence to conduction band, if we are speaking about semiconductors, this electron and hole may start attracting each other and create additional term in the total energy, and may change shapes of orbitals. So it's not the whole complete picture, but it gives you a little theoretical challenge. Why additional theories are needed for excited states? So we will not go very far today. It will be just few sketched ideas that we will expand on the next meeting. So we do need a concept of density matrix if we do want to deal with non-equilibrium phenomena and excited states. You may have noticed this object when we were exploring Hartree-Fock theory. Right? Transition from atomic orbitals to molecular orbitals and then going to total energy. The density matrix in Hartree-Fock and the one that we will be describing right now is slightly different. In considerations today and what follow, we will define density matrix as in the following way. Before, we used to have an expression that expresses total density as absolute value squares of Kohn-Sham orbitals. Please object or raise hands if you do not like this expression. Right? Absolute value square of Kohn-Sham orbitals, or orbital star without star, and then both of them depend on position, and then you add together all orbitals that are occupied, gives you density. Right? But this means that this can be reformulated as a summation, not only up to occupied orbitals, but summation up to infinity, with a weight function, which will be 1, or maybe 2 if you have doublets, singles. If your orbitals number I is occupied, and will be 0 if it is unoccupied, right? So it is expression that we have seen before. This one and this one are the same. So index is the same. There is a little star, and instead of summation until HOMO, highest occupied molecular orbitals, you make summation until infinity, and the occupation function can take values from 1 to 0. If orbital is occupied is 1, if it is unoccupied is 0. Please object if you do not like it. Do not hesitate, feel free to tell this is a bad formula, I do not like it. Anyone against this equation? Raise hands. Okay, everyone approves that it is correct. Now, who told us? Now wake up, it is an important thing. Who told us that these two indices should be the same? If we are thinking like formally mathematically, if you are building object of wave function or orbital conjugated, orbital not conjugated, product, why should we take the same? It was only our scientific intuition, but generally, formally, there are no requirements that index here and there should be the same. And more generally, we can put here different indices, I and j. Right? So make cross products of all available orbitals from our calculation. Right? You're following. Now, how do we bring this expression towards our regular expression for total density? We will set up the factors, the weight factors in front of this product in such way that it will reconstruct our original form. Like, since there are two indices here, the weight factor should also have two indices, right? If here you have I and j, here should be also I and j. We are not going to design anything new. We are going to reproduce old good DFT at the first step. So we should come back to total density, probability to find electron in a positional space. So we need to set up this weight coefficient to be 1 if the indices coincide and if the index is equal or less than whole. And if the indices do not coincide, or if you are looking to orbitals above HOMO, we should put it 0. So if we design this factor in such specific way, then this construction will reproduce as total density. So if we represent these weight factors in form of a matrix, I can probably even rewrite it. And J. So here will be block corresponding up to HOMO for I and J, and here will be above HOMO. So all elements above HOMO will be 0. So it will be rho I, J. All elements were in the off-diagonal terms, where I and J are not equal, will be zeros. So it will be a block of zeros. So right now I'm doing nothing but by practicing calligraphy of writing many, many zeros. Okay? And when both indices I and J are smaller than or equal than HOMO, then we are setting the factor equal to 1 if they are sitting on the main diagonal, and we are putting them zeros if they are sitting away from main diagonal. Or if it doesn't sound amazing, or if it sounds boring. No one objects. Everyone is fine. So, who wants to object against my suggestion to call this object a matrix? No one. Who would object against my suggestion to tell that this matrix is related to electron density? No one. Who would object to call this object density matrix? Okay? So it is a matrix of expansion coefficients or weight coefficients that helps, in a general sense, to convert pairs of orbitals into total density. Okay? And at least for the simplest case of ground state, it does work. We just set it up to a trivial values. And here I was trying to write it down. So 1, 1, 1, and everything else is 0. So if your computational model is in electronic ground state, then density matrix will be diagonal and will be 0 as far as we go above home. Just a question.
So in that equation, rho R is sum and then all that. Is rho I(j) the matrix element ij, or is it the matrix?
No. expansion coefficients in front of orbitals in general case. So if you want exact definition, rho ij will be CGCI. But we need to be careful. This would be more general than density functional theory. We are intentionally removing these off-diagonal elements compared to strict definition. Otherwise, it will be some good theory, but not DFT. Okay. Now, let me offer you another thought. If the system is deprived, delayed, removed from ground electronic state by any perturbation, would it be possible to represent it by a small correction to this ground state density? So let me write an equation like we would do for like chemical reactions. Like system in a ground state under light will be Ij in ground state plus some addition to density. Especially if the excitation has low intensity, right, then the corrections to this ground state density will be small. And everything that we will be doing in the remaining time of the semester theoretical part will be create a theory that would help us for adequate description of this little correction to the density. We are not going to all available theories to excited state. We will focus only on so-called TDDFT, time-dependent density functional theory, which is the like DFT's workhorse for ground state properties, and TDDFT's workhorse for optical spectrum. So, how to express this correction to the density function? If you are doing thermal excitations and you neglect nuclear motion, then this occupation functions, and if we still neglect off-diagonal elements, will obey the Fermi distribution. So will be a little smearing near the gap. We are approaching end of today's meeting. So I'm not going to offer any solutions and any equations to solve. We are only going through definitions. So it looks like no one was objecting to express total density as a summation of pairs of orbitals multiplied by factors. And elements of these factors are elements of density matrix. Now, there are 4 blocks in this density matrix. The block with numbers of indices I and j equal or smaller than HOMO correspond to ground state, right? To occupied orbitals that are occupied in ground state. The block of this density matrix that corresponds to orbitals equal or above LUMO will get populated only if you excite a system with high intensity laser field. If you really promote electronic occupation, and by the way, here's a little, I wouldn't say it is rigorous definition, but it's very good verbal formula. Occupations of orbitals are diagonal elements of density matrix, or otherwise, diagonal elements of density matrix are occupations of electronic orbitals. So these orbitals above LUMO become occupied only if you excite system with high intensity laser field. And these cross elements, which all of them are 0 if we do not irradiate system, they do not correspond to any occupation. But they become non-zero if your electronic system experiences, wake up and listen, experiences transition from ground to excited state. So these elements of density matrix are called transition density. And if you were exposed to TDFT theory, lift hands if you were running TDFT jobs. Okay, did you hear the word transition density?
Yes.
Okay, so transition density are these elements. And the transition density is the first order in perturbation theory if you excite system with very small intensity light. It can be insufficient to notice anything in the actual occupations. It can be as good as 0, second order in perturbation theory. But transition density will be non-zero. So in narrow sense, TDFT theory is theory of finding transition density for systems that have been irradiated by electromagnetic radiation. So just wrap your mind around these definitions and concepts, and we will slowly repeat them and get into more rigorous things when we meet next time. So, density, transition density, density matrix. Good? What else? Transition density is less than ground state, and excited state density is much, much less than ground. And if you don't have any optical distribution, the ground state is just diagonal with this F is Fermi distribution that you may have heard before. And here is, it is not rigorous, but it is an equation that sets up our mind for the future considerations. So the energy of interaction between matter and light can be expressed in dipole approximation. Dipole times electric field. And any changes to the system can be expressed in terms of this interaction. So upon exciting of the system, the in the perturbation theory, the ground state can be considered, ground state elements of density can be considered as unchanged. The transition densities can be considered as modified in the linear order compared to interaction with light. And excited state portion of the density matrix is second order. And if this mu times E is tending to 0, second order can be neglected. So this is the reason why TDFT theory, time-dependent density function theory, is formulated as a theory for transition densities. Okay, thanks much for investing your time. With this, we are finishing the meeting. I look forward to anyone who needs help towards completion of projects tomorrow. This place 6 p.m. And I'll stay here just in case any of you have questions. Meeting is dismissed. Okay, yeah, that's good. Huh?
Did I give the wrong date or something?
Yeah, I think it would be.
I didn't see it all.
Oh, please.
Any special?
I was planning.
Someone,
Okay.
I really sort of looked into that, but I really don't know. So it's at 6 o'clock?
Yes.
If I grow my hair, I tend to shave it.
Yes.
Okay, my same problem, I remember.
I might have shorter hair.
I have a question.
Do I need to look into
Yes.
your screen?